And what are the limits of integration? What are they? Huh?
Radical pi.
2.
On the bottom. On the top, it's radical pi.
And on the bottom,
It's radical pi over 2.
it's radical 5 on both of them?
Pi.
Rad pi?
Yeah. On top 2, it's rad pi.
Ah, very good. So rad pi over 2 to rad pi. Nice, nice numbers there. Good choice. Well, there's really only one thing that could possibly simplify here, and that would be to let t equal theta squared. Then dt is equal to 2 theta d theta, or 1/2 dt is equal to theta d theta. Do you see a theta d theta up there anywhere? Well, not the way it is currently written, but you'll see it there in a moment. I'm going to take theta cubed and I'm going to rewrite it as theta squared times the cosine of theta squared. And that theta cubed, well, there's 2 of the thetas, but one of the thetas I'm going to put over there with the d theta in order to parallel my substitution. What will the new limits of integration be? If I plug in radical pi over 2 for theta, then what does t become?
Square root of theta.
Well, the square root will have been squared, so the square root will be gone. It's just going to be pi over 2. When we square that, again, the square root is gone, so pi over 2 to pi. Theta squared is t. Cosine theta squared is cosine t. And the theta d theta is 1/2 dt. And I believe we just solved that one, didn't we? Somewhere? I guess I erased it. No, here it is, right here. That is the same as that, isn't it? With one difference. What's the difference between this and this? And I'm not talking about the limits of integration. Oh, wait a minute, that's an e to the t. Gosh, what's wrong with my eyes this morning? What in the world was I looking at? So we haven't done that one, but we have done that. We can do this one. I don't think that they did that as an example either. So what do you think? 7.1, integration by parts, is a good guess. Almost no matter what you say on any of these problems, that has to be a good guess. How do you think we'd set that one up?
U equals t.
And that way du becomes far more simple, doesn't it? It's just dt. And notice if we let dv equal the cosine, when we integrate it, it doesn't get any worse. So limits of integration don't change because we're not really going to u and v. This is 1/2, and now we're taking the inside of the integral and switching that to u times v, but notice we write it with the original variables, so we'll stick with the original limits of integration, minus the integral of v du dt. And all this is going to be evaluated from pi over 2. Pi. So 1/2 t sine t, and the integral of minus the sine of t? Cosine t. And this is all evaluated from pi over 2 to pi. Right, because the derivative of the cosine generates the minus sign we're looking for. Now let's plug in pi. What is the sine of pi? So this becomes 0 plus cosine of pi.
-1.
Negative 1. Minus, now let's plug in pi over 2. Sine of pi over 2?
1.
So pi over 2 times 1. Plus cosine of pi over 2? And let's see, once we get past all those minus signs, what do we have? Minus 1/2, minus pi over 4, I guess. Another nice round even number. Is that okay? When do we have a test on this stuff? Thursday? Sure, it will be fun. 41 x ln 1 plus x dx. This one, again, the complication of that being 1 plus x is not all that great. I don't know if we really have to do this substitution, but since they're recommending it, I think it would be a good idea to try. If we do this, notice that t minus 1 is x, dt and dx are equal. And the reason I wrote t minus 1 in place of x is that I need to substitute for x. So t minus 1 ln t dt. And I guess that becomes a little bit more straightforward now. I think in the reading, we once again could fall back on the integral for ln t dt. We can consider that a previously solved problem. I think on several of these problems, we've already done t ln t as well. But we haven't done it today, so I guess I have to do it. Can I erase this junk here in the middle? So, anybody remember what this was? The integral for ln t? Was it t ln t minus t? Is that right? But this one, integration by parts. Let's let u equal t, dv equal ln t dt. You like that? Is that a good choice?
Yeah.
No. Well, notice you have to integrate dv. So that doesn't look that good because I don't like that integral. Let's try swapping this around the other way. Let's try making, so let's actually put that back up there. U equal t and dv equal ln t dt. I think it's as important to know when you don't like a proposed substitution as it is to know when you do like a proposed substitution. So the way I figured out that I didn't like that is that I don't want to do that integral. I mean, I just did it here. I could write that, but that's pretty ugly. Before I just jump in and do it, it's pretty easy to investigate what would happen if you changed it. Notice letting u equal ln t is really a very good technique, isn't it? Here, when I integrate, okay, this did become a little bit worse than what I started with. I started with the t to the 1 power, I end up with a t to the 2. But notice how much more simple this becomes, right? I get rid of ln's entirely if I do that. So all of a sudden, there's no more ln in this expression. Now here I get u times v, so 1/2 t squared ln t minus the integral of v du. Oh, and that worked out real nice, didn't it? That's 1/2 t dt. So now we're done. We have 1/2 t squared ln t minus 1/4 t squared minus t ln t plus an arbitrary constant, and nothing's going to simplify.